Hello everyone, this is Kyunghwa and Hyungun. In this video, we'll discuss two remarkable papers in the field of NLP and large language models, which are Tree of Thoughts and QLoRa. We indeed live in the era of large language models. Recently, a large number of LLMs have been released by a number of companies and research groups. Originally designed to generate text, large language models such as GPT have been shown to be increasingly capable of performing a wider range of tasks. There are two main methods of utilizing language models, prompt engineering and fine-tuning. And they have both pros and cons. First of all, prompt engineering doesn't need additional data and training, and it requires only inference. However, it needs carefully crafted prompts to get high-quality output. On the other hand, fine-tuning usually guarantees higher performance compared to prompt engineering on downstream tasks. However, it needs additional data and training, indicating more time and more computational resources. Tree of Thoughts and QLoRa handle problems of prompt engineering and fine-tuning, respectively. I'll introduce Tree of Thoughts first, and Hyungun will explain about QLoRa. There are various kinds of prompting techniques, including the most basic input-output prompting and the chain of thought prompting technique, which requires a logical thought process to arrive at an answer. Here, thought is defined as a coherent language sequence that serves as an intermediate step towards problem solving. There is also a self-consistency with COT, which combines COT with an ensemble method to improve performance. However, these existing prompting methods do not allow for exploration, look-ahead, and backtracking, which are necessary to solve the various problems. Tree of Thoughts is a new prompting method for language model inference. TOT frames any problem as a search over a tree, which each node is a state representing a partial solution with the input and the sequence of thoughts so far. A specific instantiation of TOT involves the following four factors, and let me explain each of them in detail. First factor is thought decomposition. TOT leverages problem properties to design and decompose intermediate thought steps. Depending on different problems, a thought could be a line of equation, a couple of words, or a whole paragraph of writing plan. In general, a thought should be small enough so that language models can generate promising and diverse samples, yet big enough so that language models can evaluate its prospect towards problem solving. Second factor is thought generation. Given a tree state consisting of an input and intermediate thoughts so far, we can consider two strategies to generate candidates for the next thought step. First, thoughts can be sampled IID from a COT prompt. This works better when the thought space is rich and IID samples lead to diversity. Second, thoughts can be proposed sequentially using a propose prompt. This works better when the thought space is more constrained, so proposing different thoughts in the same context avoids duplication. Third factor is state evaluation. Given a frontier of different states, the state evaluator evaluates the progress they make towards solving the problem. In this paper, the authors use a language model to deliberately reason about states. And there are two strategies of state evaluation. First strategy is to value each state independently, where a value prompt reasons about the state to generate a scalar value or a classification that could be heuristically turned into a value. Second strategy is vote across states. When problem success is harder to directly value, it is natural to instead compare different partial solutions and vote for the most promising one. This is similar in spirit to a stepwise self-consistency strategy. Fourth factor is search algorithms. Within the TOT framework, one can plug and play different search algorithms depending on the tree structure. In this paper, the authors explore two relatively simple search algorithms, BFS and DFS, leaving more advanced ones for future work. The two search algorithms incorporated in TOT framework are illustrated as in the figures. BFS maintains a set of the B most promising states per step. This algorithm is used where the tree depth is limited and initial thought steps can be evaluated and pruned to a small set. On the other hand, DFS explores the most promising state first until the final output is reached or the state evaluator deems it impossible to solve the problem from the current state. This algorithm employs pruning and backtracking for efficient exploration and search over a tree. This paper conducted experiments on 3 tasks that are hard even when sampling from the state-of-the-art language model, GPT-4, using standard I/O prompting or chain-of-thought prompting. First, Game of 24 is a mathematical reasoning challenge where the goal is to use 4 numbers and basic arithmetic operations to obtain 24. Creative writing is a task where the input is 4 random sentences and the output should be a coherent passage with 4 paragraphs that end in the 4 input sentences respectively. Finally, for 5x5 mini crosswords, the input describes the 5 horizontal clues and the 5 vertical clues, and the output should be a board of 25 letters to solve the crosswords. Experiments are performed using a chat completion mode GPT-4 with a sampling temperature of 0.7. Next, let me explain how the TOT framework is applied for problem solving of each task. To frame Game of 24 into TOT, it is natural to decompose the thoughts into 3 steps, each an intermediate equation. The authors perform BFS in TOT for this task, where at each step they keep the best 5 candidates. At each tree node, they extract the remaining numbers and prompt the language model to propose some possible next steps. The authors prompt language model to evaluate each thought candidate as sure or likely or impossible with regard to reaching 24. Language model evaluates the last step as only sure or impossible. Values are sampled 3 times for each thought, and the cumulative values are used for the search algorithm to decide which states to explore. As shown in the table, TOT with a breadth of 1 already outperforms the existing prompting methods. Figure B breaks down at which step COT and TOT samples failed the task. Notably, around 60% of COT samples already failed the task after generating the first step, or equivalently, the first 3 words. This highlights the issues with direct left-to-right decoding. For the task of creative writing, the authors build a TOT with depth 2 and only 1 intermediate thought step. Language model first generates 5 plans and votes for the best one, then similarly generate 5 passages based on the best plan, then votes for the best one. The results show that TOT achieves higher scores both on GPT-4 evaluation and human evaluation compared to I/O and COT prompting. For the task of mini crosswords, each thought step is a predictive word and its position. The authors leverages a DFS algorithm that keeps exploring the most promising subsequent word clue until the state is no longer promising. For thought generation, the authors prompt a proposer prompt 5 times and also prompt a language model each time to give a confidence level for different thoughts and aggregate these across proposals to obtain a sorted list of next thoughts to explore. Then the authors use value prompt to evaluate for each clue if it is possible to fill given the constraints. If any remaining clue is deemed impossible to fill in, then the exploration of the state subtree is pruned and DFS backtracks to its parent node to explore the next promising thought. The authors limit DFS search steps to 100 and simply render the deepest explored state into the final output. As shown in the table, TOT significantly improves all metrics, achieving a word-level success rate of 60% and solving 4 out of 20 games. Such an improvement is not surprising, as I/O and COT lack mechanisms to try different clues, make changes to decisions, or backtrack. In conclusion, TOT allows language models to perform deliberate decision-making by considering multiple different reasoning paths and self-evaluating choices to decide the next course of action, as well as looking ahead or backtracking when necessary to make global choices. TOT has a lot of advantages. First, TOT is a generalized framework of existing prompting methods. Second, the base LM, as well as the thought decomposition, generation, evaluation, and search procedures can all be varied independently. Third, different problem properties, language model capabilities, and resource constraints can be accommodated. Finally, no extra training is needed, just a pre-trained language model is sufficient for TOT. However, TOT also has limitations. First, deliberate search such as TOT might not be necessary for many existing tasks that GPT-4 already excels at. Furthermore, TOT requires more computational resources than sampling methods in order to improve task performances. This is the end of explanation for TOT paper, and Hyunggun will introduce QLoRa.
Hi, my name is Hyunggun Lee, and I will presenting the next paper titled QLoRa, Efficient Fine-Tuning of Quantized LLMs. For example, an LLM with 65 billion parameters, such as Llama, requires more than 780 gigabytes of GPU memory. Then, can we fine-tune a 65 billion parameter Llama on a single GPU with only 48 gigabytes? This paper argues that it is indeed possible to train effectively on a single 48 gigabyte GPU by using a method proposed in this paper called QLoRa. QLoRa combines the concepts of quantization and LoRa. To elaborate, QLoRa quantizes the weights of the pre-trained LLM, storing them in a proposed 4-bit normal float format. During weight updates, the quantized 4-bit weights are converted to 16-bit brain float format to be compatible with LoRa, which uses 16-bit brain float. Let's first explore some background of quantization. Quantization is a technique used to convert input tensors from a higher bit type to a lower bit type. For instance, to change a 32-bit floating point type to an 8-bit integer type, the highest value in the input tensor is utilized. This value normalizes the tensor to a range between -1 and 1. Subsequently, the tensor is multiplied by 127 to adjust the values to fit within the -127 to 127 range of an 8-bit integer. The highlighted blue part represents the quantization constant, which is crucial during the quantization process. However, if there are outliers in the input tensor, they can cause other values to aggregate during normalization. This aggregation leads to inefficient quantization. Therefore, by dividing the entire input tensor into blocks of size b and creating n such blocks, the issues caused by outliers are significantly mitigated. Each block is quantized separately and it generates its own quantization constant. According to the QLoRa paper, a block size of 64 is used when quantizing the LLM weight tensor. LoRa is a method to mitigate the high costs associated with fine-tuning LLMs for specific tasks. LoRa involves freezing the existing pre-trained weights and only adding and training linear layers highlighted in orange in the diagrams and equations to proceed with LLM fine-tuning. In QLoRa, the first step is to optimally quantize pre-trained weights into the 4-bit normal float data type. Secondly, they use a double quantization method to reduce the average memory footprint. Lastly, a page optimizer is employed to prevent GPU memory spikes. Firstly, the 4-bit normal float is an information theoretically optimal data type proposed based on the concept of quantile quantization. Quantile quantization assigns quantiles so that each quantization bin matches the same number of data points. However, estimating quantiles for every different distribution is computationally expensive. To address this issue, the paper proposes a method that applies quantile quantization to a single fixed distribution. This approach is based on the assumption that the weights of the pre-trained model generally follow the normal distribution. For a normal distribution with mean 0 and variance 1, we estimate 2 to the power of k plus 1 quantiles as shown in the equation below. These values are then normalized to fit between -1 and 1. After that, the input weight tensor is quantized within the range of -1 to 1. These methods minimize information loss and efficiently quantize the input tensor to 4 bit. Additionally, to ensure a discrete 0 point of 0, the quantiles are divided asymmetrically, not symmetrically. The division is illustrated with the negative part split into 2 to the power k-1 parts. The positive part is divided into 2 to the k-1 plus 1 parts. Quantization is then applied to each part accordingly. Secondly, QLoRa uses a double quantization method. Each block of 64 weight tensors is quantized to 4 bits, with a quantization constant for dequantization. This constant is stored separately outside the model in 32 bits to facilitate operations between the 4-bit model and 16-bit LoRa. Constructing 64 blocks in 32 bits requires an additional 0.5 bits per weight, totaling 4.5 bits per block. By requantizing the 0.5-bit quantization constant to 8 bits, memory use is reduced. For quantizing from 32-bit floating point data type to 8-bit floating point data type, an additional 256 block size can be utilized. The extra memory drive from the secondary quantization constant results in a final 0.1 to 7 bit. This reduces the number of bits from 4.5 bits to 4.1 to 7 bits. Lastly, page optimization is a method that automatically allocates page memory between the CPU and GPU as needed. When the GPU experiences out-of-memory issues, the page memory is moved to CPU RAM. When more memory is required by the optimizer, it is reassigned back to the GPU. This process helps prevent memory spikes in the GPU. The formula depicted involves the calculation between the 4-bit quantized pre-trained model weights and the 16 adapter. After double quantization, the parameters are updated in a calculation with 16-bit LoRa. Next are the results comparing the proposed QLoRa method with standard fine-tuning. Using an alpaca dataset, fine-tuning a 7 billion parameter lemma with 4-bit normal floats via QLoRa showed better performance than 16-bit full fine-tuning. Additionally, comparisons were conducted across 3 scenarios for various model size. In all 3 cases, QLoRa matches the performance of 16-bit full fine-tuning and fine-tuning using LoRa. Next, the results comparing the 4-bit normal float data type with other 4-bit data types are discussed. The 4-bit normal float data type significantly improves performance. Double quantization reduced the memory footprints. Lastly, since QLoRa showed meaningful results, the paper introduces the state-of-the-art chatbot Guanaco. It was developed for consumer-grade GPUs using the QLoRa method. The performance of Guanaco is compared with ChatGPT on the Vicuna benchmark. The Guanaco model was trained using QLoRa method on the OASST1 dataset. Finally, these are the conclusions of this paper. Thank you for listening.